Okay. So again, section 3.3 or 3.6, graphs of functions. Our learning objectives in this section are we're going to be able to utilize vertical line test, which I sort of taught you guys ahead of time so that this section can be a little more straightforward for you guys. We'll also be able to identify graphs of basic functions, and then we'll be able to learn how to read information from graphs of functions. On Monday, or this past Monday, we learned about relations and determining whether they were functions or not. So we learned about that formal definition of a function, really making sure that you have a unique x value, a different x value, so that it passes that vertical line test. That's why they have all of these dashed vertical lines here, to make sure that these vertical lines only hit our function in exactly one spot. And if it does, then we indeed have a function. Our formal definition of a vertical line test is as follows, and then I'll maybe have a student read this for us. So Caesar, do you want to read it for us?
Vertical line test, a set of points in a regular coordinate system is the graph of wave functions. Every vertical line intersects the graph in at most one point. If any vertical line intersects the graph in more than one point, the graph does not represent a function.
Beautiful. And so the main focus in this class is really utilizing that vertical line test from a graphical standpoint. So let's get into it. Example 1, does this pass the vertical line test? Yes. What about in example 2? No. Right? It hits at 2 spots almost everywhere. We have another notes slide, which you've seen once again before, but it's always good to really reinforce this notation. But f of x is just another way of saying your output value. This is known as function notation. And why do we utilize that? Well, we can clearly see what our input value is. And so it tells us if we input this value of x, we're going to spit out a function, an output value. In coordinate form, we have this x comma f of x, but it's the same as just x comma y. And then this is just another notes page, really honing in on our special types of functions, which are linear functions. Remember how I told you guys last class that all lines are pretty much linear functions. The only exception is what type of lines? What's the only line that fails the blank line test? Yeah, so all vertical lines are not functions. But any other type of line in the world is. We also once again see our famous slope-intercept form, our y equals mx plus b, but in this case, in function notation, our f of x equals mx plus b. And then we are able to identify that our domain and our range, there are no restrictions here. We have all possible x and all possible y values, negative infinity to positive infinity. Right. Example 2, we are now asked to graph this function f of x is equal to negative 2x minus 4. Again, this is the same as just y equals negative 2x minus 4, which is very similar to our slope-intercept form, y equals mx plus b. Can easily identify what our slope is here, as well as what our y-intercept is. What's our slope? Yeah, and what's our slope as a fraction? Beautiful. Our rise over our run. What's our y-intercept? And what's our y-intercept as a coordinate point?
-4. I don't know. 0.
Yes, 0, -4. Excellent. Right, definition of y-intercept is always when x is equal to 0. Anytime we graph, we want to graph our y-intercept first. 0, -4. This is our starting point. And then we're utilizing our slope to plot additional points. Our rise over run, -2 over 1. No, it's not rising, it's actually deflating. We're going down 2 over 1 each time. Down 2 over 1, plot a point. Down 2 over 1, plot a point. Down 2 over 1, plot a point. If you wanted to go in the other direction, you would have to go left 1, up 2, plot a point. Left 1, up 2, plot a point. I mean, I plotted a bunch just to practice with you guys, but as long as you usually plot like 3 points, you should be good. 4, you're definitely good. And then your last step when you're graphing, you really need to make sure that you write your function, you're labeling your function on your graph. Lucky for us, we already had a proper scale in place and we already had our x and y axes labeled. But on the exam, that won't be the case. As well as quizzes, that won't be the case. You really need to make sure you put in a proper scale, you label your x and your y axis, you label your function, and then you plot at least 3 points for lines, usually 4 points for parabolas. And then you're done. That will give you full credit for a question like this. This is another notes page known as a constant function, aka our horizontal lines. Our y is equal to some number. It's a function because it passes the vertical line test. It's just not known as a special function because it fails the 1-to-1, aka the horizontal line test everywhere. And a cool thing to note, our domain is still all real numbers, but our range is just one specific point. It's just whatever this y value is. In this case, we are denoting it as our b. Okay. So now let's practice our constant functions. We're now asked to graph f of x is equal to 4, also known as y equals 4. All you have to do is find 4 on your graph. Again, make sure you're properly labeling your x and y axes as well as your scale. And then you label your graph as well. I'll put it in function notation too. And that's it. We're done. Next type of famous function we're going to look at is known as our identity function. And why is it called identity? Well, it's because all of our y's are equal to all of our x's. Once again, in function notation, this is just f of x is equal to x, which is in y equals mx plus b form. Our y-intercept is just at 0, so our b is 0, and then our slope is just 1. We're going up 1 over 1 every time. Example 4, we're now jumping into a higher degree. Our exponent is now 2, and these are known as quadratic functions. This is our famous quadratic function. And in later sections, we'll actually go into full detail on how to graph a bunch of different types of quadratic functions. We'll learn about finding an axis of symmetry, finding a vertex point, plotting points to the left of the vertex, to the right of the vertex, knowing, is my shape going to be U-shaped, right side up, or is it going to be an upside down U based off of the coefficient in our quadratic formula? But this is still the very beginning before we get into detail of quadratics. So in this case, I just want you guys to resort back to your old-fashioned X and Y table and choose some good X points so that you can figure out, okay, are we looking at a U-shaped or an upside down U? So some famous points that you should always really include in your X values are usually 0, -1, and +1. And then from there, you can just choose any number higher than 1. I'm just going to choose 2 in this case, and any number lower than -1. I'm going to choose -2 to keep it simple. And now what we do, how do we find that Y value? We just take this X value and plug it in and solve. So -2, remember, it's parentheses. So -2 in parentheses squared gives us a +4. -1 in parentheses squared gives us a +1. 0 in parentheses squared gives us a +0. 1 in parentheses squared gives us a +1. And 2 in parentheses squared gives us a +4. So now we're going to go ahead and plot these points. We have -2, comma, +4. We have -1, comma, +1. We have 0, comma, 0. We have 1, comma, 1. And we have 2, comma, 4. So we have an upwards U, which tells us that our vertex, so known as our minimum in this case, is at the origin, 0, comma, 0. Last but not least, we need to make sure we're labeling the function on our coordinate plane. This is indeed f of x is equal to x squared. And then we're done. This is just the solution of what we just sketched out, our famous quadratic function. Another synonym of our famous quadratic is known as our square function. It's just a little bit more specific. All right, AKA our famous quadratic function. Other words you might see pop around are parent function or toolkit function. That one you don't see as often. A lot of these administrators like implementing new vocabulary in the mathematical world, which certain ones I can agree with, but others I feel like they just have nothing else to do with their time. But okay. And then the last thing that I want to mention, once again, our domain and our range. Our domain really emphasizes on what are all the possible x values in this graph. We have no restrictions here. We can have any x value in the real number system, which is why we have all real numbers, which is known as negative infinity to positive infinity. This is just a way to identify all real numbers in math notation. If they don't ask you to specify, put in interval notation, you can write it as this and get full credit. I would say in this class, 99% of the time, they're going to ask you to put it into interval notation. And then the range is all of our possible y values. So the lowest y value we can have is 0, which is why we have a hard bracket. We're including that boundary, and then it shoots up to infinity. Let's try another example together. This time, we're once again looking at a cubic function. All of these shapes that we're going over today, you should really practice them and get them to memory, because especially when you jump into pre-calculus, you want to know these shapes so that you're able to easily identify the transformations of graphs that are very similar to their parent functions. And so I already know straight off the bat it's going to look like something like this. But at this moment in your math career, you want to once again just pick good values so that you can graph the coordinate points and connect the dots. So once again, 0. I'm going to choose -1, +1, and then we'll once again do -2, +2. Plug it in. -2 cubed actually remains negative. -2 times -2 times -2 gives you -8. -1 cubed is -1. 0 cubed just stays as 0. 1 cubed is +1, and 2 cubed is +8. So let's plot these points. We have -2, comma, -8. -1, comma, -1. 0, comma, 0. 1, comma, 1. And 2, comma, 8. And then we're going to connect the dots. And you'll see that we have exactly what I sort of sketched out in green earlier. Last but not least, you once again want to make sure that you label your function on your coordinate plane so you can get full credit for this problem. X, y-axis, proper scale. Plot your points, connect the dots, put the arrows, and label your function, and you're done. Okay. And this is once again just sort of the answer key to what we just did in example 5. And another special name, is known as our cube function. All right, our famous cubic function. Domain and range, we have no restrictions here, so we have all real numbers. Ooh, now we're looking at roots. This is our famous square root function. Again, show you what this looks like in a sketch. Something like this. But at this level in your math career, pick good X values, plot points, connect points, and then graph. Probably don't need that many points here. We can't take the square root of a negative. Well, we can, but it would be imaginary. And we're dealing with real numbers right now. So the lowest value that we're working with here is 0. And then we can go up from there. 0, 1. I want to pick strategic X values to make my calculations easy. So if I picked 2, it would be hard for me to find the square root of 2. So I kind of want to focus on choosing perfect squares. The next value should be 4. That's a perfect square. So is 9. So is 16. Square root of 0 gives you 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 3 is, or square root of 9 is 3. And square root of 16 is 4. Probably won't be able to plot that last point. So we have 0, 0. We have 1, 1. We have 4, 2. And then we have 9, 3. Connect the dots. Draw your arrow. Label your function. This is our famous square root function. F of x is equal to square root of x. And then we're done. Our domain here, our lowest possible x value is 0. And then it shoots to infinity. And then our range is actually the same thing. Right? We can't have any negative y values here. So our range is from 0 to infinity as well. This was just the answer key. Right. Absolute value. I want to see how many slides we have left. About 7 slides left. Okay. Absolute value is going to look like a V. Once again, let's choose good X values. -2, -1, 0, 1, 2. Absolute value of -2 is 2. Absolute value of -1 is 1. Absolute value of 0 is 0. Absolute value of +1 is 1. And absolute value of +2 is 2. This is known as our famous absolute value function. Plot our points. Connect the dots. Write your function. Our domain. We have no restrictions, so we have all real numbers here. Our range. We can't have any negative y values, but we can have 0, so we include 0 all the way up to positive infinity. Once again, have our answer slide. So we have a note slide. Maybe I'll have 3 students read for me. Let's see, Anna, I'll have you read the yellow. And then Gabriella, I'll have you read the blue. And then Emmanuel, I'll have you read the pink. Okay.
In the science data is often collected and then graphs. The graph is analyzed. Information is obtained from the graph, and then often predictions are made from the data.
Remember, the domain is the start of all the x values in the order paired in the function. To find the domain, we look at the graph and find all the values of x that have a corresponding value on the graph. Follow the value x up or down vertically. If you hit the graph of the function, then x is the domain.
Good.
Remember, the range is the set of all the y values in the ordered pairs in the function. To find the range, we look at the graph and find all the values of y that have a corresponding value on the graph. Follow the value y left or horizontally. If you hit the graph of the function, then y is in the range.
Awesome. Great work. Okay, so what we had on the previous slide is sort of what they're demonstrating visually on this slide. If you draw a vertical line and it hits your function, then that is a value in your domain. Now, if you draw a horizontal line and that hits onto your function, then you have this y value as part of your range. A lot of this is just repetition that we've been really building over these past few weeks. Okay. So let's look at this example 8 to identify what is our domain and what is our range. There are no arrows at the end of this graph, which means we're going to have some endpoints. Right? What's our lowest possible domain? -3. And what's our highest possible domain? AKA our x value. Yeah, +3. We're including both of those values. So our domain is just -3 to 3. What about our range? What's our lowest possible y value? Yeah, -1. And what's our highest? +3. So -1 up to 3. And we're done. So we want to use the graph of the function to find the indicated values. And so we have a bunch of different parts. The graph is on this side, but I also screenshotted all of these problems so that we could see it. And so f of 0, we're just looking for when our x value is 0, what is y? This is also a very common question on exams and final exams. I see it almost every single time. So f of 0 gives you what? It's just 0. What about f of 3 over 2 pi? Well, 3 over 2 pi gives us what as our y value? Yep. What about negative 1/2 pi? Now we're over here. It's our y value. -1 again. We want to find the values of x for when f of x is equal to 0, aka when y is 0. So what are all of our values of x that hit our x-axis? We have -2 pi. We have negative pi. We have 0. We have positive pi. And we have 2 pi. Then it says find the x-intercept. So D and E are very similar. But when it says find the x-intercepts, you want to put it into coordinate form. So we're looking at 0, comma, negative. Sorry, it's the other way around. Definition of x-intercept is when y is 0. So we have -2 pi. And maybe I'll make the pen a little thinner. Comma 0. What's our next x-intercept? Good. Keep going. 0, comma 0. Pi, comma 0. And our last one, 2 pi, comma 0. Awesome. Y-intercept. What's the only point that hits our y-axis? Yeah. Find the domain and write it in interval notation. What's our domain here? Look at all of our possible x values. Do we have any restrictions anywhere? No, so it's -infinity to +infinity. And then last but not least, what's our range? What's our lowest possible value every single time? -1. And what's our highest? +1. Right. And we're done. Any questions on this page at all? This was the last example from this section. We will start chapter 4 tomorrow, right? We have class tomorrow, but let me stop recording this.